Okay, so by now you should have generated a graph using the data you got from Pivot of a puck sliding down a ramp. Um, your graph should have data points, which we can see down here in this graph. It should have a line of best fit, which we can see traveling up in a curve there. Um, and so here we see one of your fellow students' graphs. Um, the line of best fit is y equals 56 times x, which is the same as y equals 56 times x squared. The puck mass was 180 grams and the ramp angle was 7 degrees. So what if we change the mass? How is that going to change the graph? Well, here is another graph made by another student with a puck mass of 420 degrees, same ramp angle. This student found their best fit was y equals 55.4 times x squared, which is remarkably close to y equals 56x squared. So it seems like changing the mass doesn't change our equation. The thing that seems to matter, maybe, well, the thing that doesn't matter is the mass. Maybe the ramp angle matters. So what if we change the angle? Okay, here is a steeper ramp, same mass. Well, no, actually, we've gone back to 180 degrees, 13-degree ramp, and our graph has gotten a little steeper. Our M value now is 99, so that's gone up. Let's make it a little steeper still. And here we have a ramp angle of 16 degrees and y equals 134x squared. So we're seeing a trend here. Steeper ramp, faster acceleration. Faster acceleration results in a steeper parabola and a bigger m value. So I'm going to switch gears here. I want us to think about velocity for a second. I want us to think back to the bowling ball lab. And when we graphed as the bowling ball moved at a steady pace, a steady velocity across the track that it was rolling on, we got a steady line. So I want to know, how fast is the bowling ball moving at 1 second? Well, here's 1 second. Between 0 and 1, it moved, y-axis, it moved about 56 centimeters in 1 second. Now notice our m value, 56.5. So in fact, on a graph like this, our velocity, or how fast the bowling ball is moving at 1 second or at 2 seconds or at any time, is 56.5 centimeters per second. So here are some equations that relate. Velocity is time as distance divided by time. Now we can look at that in a big scale. I went 180 miles in 3 hours. My average velocity was 60 miles an hour, but I didn't maybe go 60 miles an hour the entire time. Maybe I stopped for gas, and maybe I went 75 for a while to try to make up the time. So we also need to think about instantaneous velocity, the velocity at some moment. And we could figure that out by considering the distance something goes over a very small period of time. We're going to see how this relates to our puck sliding down a ramp in just a moment here. So I'm going to ask again, how fast is the puck going at 1 second? This is one of our graphs. So here we are, 1 second, how fast is the puck going? I want us to focus on the region right around 1 second. And we can click on these data points and we can actually get, times for these 2 points and distances. We can kind of pretend it looks pretty straight, like if this is all we were looking at, we might think this was a graph of a straight line. So we're going to figure out what a straight line would look like through the 2 points on either side of 1 second. Remember that slope is rise over run, how far up we go divided by how far over we go. In other words, here's our fraction, here's our ratio, if you will. Now I've taken 136 minus 97 over 1.0833 minus 0.9167. So I've got my rise, the difference in y, divided by my run, the difference in x. Do all those calculations, and I come up with a slope of 234. And I'm going to draw it for you. So at the 1 second mark, our sort of simulated straight line slope is 234 centimeters per second. Now, that's an interesting number. First of all, acceleration is change in speed. That is really what it means. Speeding up or slowing down, it's change in speed. At time 0, our speed was 0. The thing hadn't started moving yet. At 1 second, our speed is 234 centimeters a second. So over that second, our change in speed is 234 centimeters. 234 centimeters per second over that 1 second. Now, wording's going to get a little awkward here. Bear with me. We can also say acceleration is 234 centimeters per second every second. Or acceleration is 234 centimeters per second per second. Or acceleration is 234 centimeters per second squared, which is in fact, the centimeters per second squared is the units that we use to talk about acceleration. In the same way we use centimeters per second to talk about velocity, or centimeters to talk about distance. What do I got? Oh, this is the interesting thing. Notice that 234, our velocity at 1 second, is twice of 117, the m value for this parabola, which implies that our equation y equals 117x squared, the equation for the parabola, could also be considered to mean, now remember, y is the distance that the puck traveled. The distance is 1/2 times our acceleration value of 234 centimeters per second times time squared. So that's something to consider. We're going to actually file this away in our in our notebook as one of our equations that we're going to be able to use. And again, bigger distance is 1/2 times acceleration times time squared. Another thing I want us to consider is, how does the distance of the puck change as the time doubles? So here we have time, where are we? 0.25. We're looking at time 0.5 and time 1. So from 0 to 0.25 is 1/4 of a second. And then we're going to double that to 1/2 a second and double that to 1 second. Now, if we were to go back to our straight line bowling ball rolling across a track, as I double the time that it travels for, the distance doubles along with it. If I go, for 1 second, it's going to go 56.5 centimeters. If I go for 2 seconds, it'll go for 2 times 56.5 centimeters, or 100 and whatever that is, 113 centimeters in 2 seconds. Here, though, something different happens. So at 0.25 seconds, we've gone 7 centimeters. At 0.5 seconds, we've gone 29 centimeters. At 1 second, we've gone 116 centimeters. Now, 7 times 4 is 28, which is very close to 29 centimeters. 29 times 4 is 116. So what this suggests is that as the time doubles, as we go from a quarter second to a half second, the distance is quadrupled. And as we go from a half second to a whole second, the distance quadruples again, which is what brings us to the name for this equation, for this relationship, is a quadratic equation. Now, this doesn't matter. This is where I'm going to stop here with our quadratic.